Hello everybody and welcome to this online series of lectures on undergrad level introductory course on quantum mechanics. I am Fahil Hashmi and I teach in ComScience University Islamabad Lahore campus. In these lectures I will try to present quantum mechanics in a manner that is different from how the subject is usually taught in textbooks. I hope that you will find my approach interesting and easy to understand. The plan for this lecture is as follows. We will first look very briefly at the need for quantum mechanics. Then we will try to answer the question what is quantum mechanics. This will give us an interesting insight into the working of nature. And finally, we will look at a few simple examples, see how they behave in nature and how quantum mechanics accounts for their behavior. The lesson we will learn in this lecture is that quantum mechanics make use of linear algebra with its vectors and operators, matrices, and so on. This lecture mostly consists of the material I have discussed in my blog at these two posts. Let's start with the need for quantum mechanics. In science, we are in a continuous need of new theories as we always seem to have unanswered questions with all the theories that we have. The situation becomes more urgent if we have experimental observations that cannot be explained with the existing theories or are in clear contradiction with the available theories. This was the case in the late 19th and the beginning of the 20th century. The established theories of the time were Newtonian mechanics to describe material particles and Maxwell's equations to describe electromagnetic radiation. Collectively, these two constitutes classical physics. At the turn of the last century, there were a number of experimental observations that could not be satisfactorily accounted for using classical laws and reasoning. These include the photoelectric effect, in which light of suitable wavelength could eject electrons from metals. The final details of the process were against the predictions of classical light-matter interaction. Then there was the black body radiation problem. The radiation from a hot source plotted as the function of the frequency of the radiation could not be explained. We had Compton scattering, in which X-rays scattered from a target exhibited change in their wavelength as a function of the scattering angle, suggesting that these rays were consisting of particles having definite energy and momentum. The stability of atom itself was an open question. It was known that atoms have a massive positive charge in the center and that negative electrons are distributed around the center. The stability of such configuration was not evident. There were numerous other experimental observations for which we did not have satisfactory answers. The students listening to this lecture are encouraged to read about these experiments in their favorite modern physics book, and they should try to identify the features that could not be explained with the existing theories of the time. As a side note, we should mention that there were few insights into the new quantum behavior in the form of Bohr's atomic model, the de Broglie hypothesis, space quantization, Sommerfeld's model for atomic orbits, etc. We now call these collectively as the old quantum theory. However, this was still not a satisfactory explanation for all the other phenomena, and the need for a fully consistent, satisfactory theory remained there. Finally, such a theory was formulated in the first quarter of the last century, and we will learn about this new quantum theory in the remaining part of this and the forthcoming lectures. Now consider the question, what is quantum mechanics? One may argue that this is not the right time to ask the question as we have yet to learn the theory. However, I believe that the question can be answered in a manner that gives us an insight into the working of the nature and also provides a guiding principle that will help us understand the theory better. I prefer to answer this question as follows. Quantum mechanics is a theory that allows us to calculate the probabilities of random events happening in nature at the fundamental level. By the fundamental level, I mean the level at which we deal with the building blocks of matter and energy. These blocks are atoms, the subatomic particles, molecules, photons, etc. Nature at this level behaves very strangely. One peculiar aspect of the nature at this level is that it is completely random. The interactions of the building blocks going on at this level cannot be predicted with certainty. For example, we know that an excited atom will emit a photon and will come to its ground state, but we cannot know when this will happen or in which direction the emitted photon will go. Or if a nucleus of an atom is bombarded with a proton, neutron, and an alpha particle, we do not know whether the incident particle will bounce back, scatter off, or continue its journey without interaction. There are other examples as well of these sort of interactions. These are random events and cannot be predicted with certainty. In fact, it can be argued that the true randomness exhibits itself in nature only in these fundamental interactions, and all other phenomena that we call random is actually pseudo-random. This is the point where we should recall the famous quote by Einstein that says that God does not play dice. However, it seems that God actually does. So, coming back to our question, when all the interactions going on in nature at the fundamental level are random and cannot be predicted, what we can do is calculate the probabilities of these events. This is what nature let us do, and quantum mechanics teaches us how it's done. Now we will look at a few simple examples and see how quantum mechanics helps us work out the probabilities we have just discussed. Consider a beam splitter. It is a simple optical device that splits a beam of light falling on it. Part of the light gets reflected, another part is transmitted. We know that a light beam consists of a large number of photons. So when we have a large number of photons coming from the source, the beam splitter will reflect some photons toward this direction, which will be detected by D1 and let the others pass through. Now suppose we have a single photon coming from the source S. Let's ask ourselves a very simple question. Will the photon be reflected and detected at the detector D1, or will it be transmitted through the beam splitter and detected at D2? You will be surprised to know that there is absolutely no way to answer this question. This is the kind of random interaction we were talking about. Nature does not allow us to know if the photon will be reflected or transmitted. We will have to change the way we ask questions if we wish to probe the nature at the level of single photons. Let's actually perform the experiment in which a photon is emitted from the source and record if it is detected by the detector D1 or D2. Now repeat the experiment a large number of times, say n. For each run of the experiment, we keep track of the detections at D1 and D2.
Let's say that the number of times it is reflected and detected by detector D1 is NR, and the number of times it is transmitted and detected by D2 is NT.
The numbers NR and NT reveal the reflection and transmission properties of the beam splitter. For example, if NR is large compared to NT, we know that the beam splitter reflects more particles toward D1 and let few to transmit through to D2. In the limit of large n, the ratio NR over N is the reflection probability and NT over N is the transmission probability. Let's write these two as R square and T square. Obviously, we have R square plus T square equals 1. In this way, we have established that for this beam splitter, a photon has R square probability of being reflected and T square probability of being transmitted. This is all the description we can have for this simple system. We also see that in quantum world, we can probe the nature by asking for the probabilities of different events instead of asking which event will occur. Now let's look at a different system. We have placed another beam splitter over here, which is identical to this beam splitter and has same reflection and transmission properties. And we have introduced two perfectly reflective mirrors along these two paths of the photon. This arrangement is called an interferometer. Again, consider a single photon coming from the source S. The photon, after passing through the system, will be detected at one of these detectors. And we have already learned by now that we cannot ask or tell which detector will detect it. Instead, we ask the question, what is the probability that the photon will be detected by D1? Let's try to work out this probability from what we have learned in the previous example. Remember that both these beam splitters have R square probability of reflecting the photon and T square probability of letting it pass through. So the photon coming from the source has R square probability of reflection over here and another R square probability of the second reflection at this second beam splitter. The probability that the photon goes through these two reflections is R raised power 4. The photon can also be detected at D1 if it is transmitted through both beam splitters. The probability of this event is T raised power 4. This makes the total probability of the detection of the photon at D1 to be R4 plus T4. Similarly, we can work out the probability of the detection of the photon at the detector D2. To reach D2, the photon will have to be either reflected here and transmitted here, or transmitted here and reflected at the second beam splitter. Both these events make R square T square contribution to the probability of detection of the photon at D2, which according to our reasoning should be 2R square T square. We can check these computed probabilities by performing the experiment a large number of times in which a photon is emitted from the source and is detected by D1 or D2. And if we do this, we will see that these probabilities are wrong. The correct probabilities we get from experiment are T square minus R square whole square for detection at D1 and 4R square T square for detection at D2. This means that the way we have calculated the probabilities is flawed and we are missing something. We can get some insight into the problem by focusing on these probabilities. This probability will be 0 for an interferometer for which R square equals T square, and for such interferometer this probability will be 1. This means that all the photons coming from the source will be detected at D2 and none will be detected at D1. This reminds us of interference-like phenomena with constructive interference along the path to the detector D2 and destructive interference towards D1. This gives us the idea to think in terms of amplitudes that flow along these two arms, interfere at the second beam splitter, and give rise to experimentally verifiable probabilities. We will see next that indeed this is true, and in order to work out these amplitudes and associated probabilities, we will borrow tools from linear algebra. The tools we will use are vectors and operators. We associate column vectors to describe the state of the photon in the following manner. The path shown below in the figure where the photon remains on the left side of the two beam splitter is one state of the photon, and we associate it with the column vector 1, 0. Similarly, we associate the column vector 0, 1 to the state of the photon when it is following the path shown red in the figure. The state of the photon on its way from the source to the detector is modified by the two beam splitters. The action of both beam splitters is given by the matrix iota r t p iota r. Iota is the square root of -1 and r and t are related to the reflection and transmission properties of the beam splitters. The students must appreciate that this is very different from how they have been doing physics in all their previous courses. This brings us to the important lesson of this lecture. Quantum mechanics makes use of linear algebra. The states of quantum systems are described by vectors, and these vectors evolve under the action of operators. Now we will see how the vectors and operators account for correct detection probabilities. Here is the time evolution of the photon. Immediately after being emitted from the source and before the first beam splitter, the state is still the column vector 1, 0, telling us that the photon is on the left side of the first beam splitter. At the first beam splitter, the following action takes place. This is a matrix multiplication. We have the matrix for the beam splitter, the state of the photon before the action of the beam splitter, and the state of the photon after the action of the beam splitter. This new state corresponds to the time interval when the photon is inside the interferometer, that is between these two beam splitters. This state is what we call a superposition state. It can be written as the linear combination of the vectors we have associated with the two paths. Iota rt equals iota r times 1, 0 plus t times 0, 1. Here iota r and t are the expansion coefficients. We know that the vector 1, 0 means that photon is along this path, and the vector 0, 1 means that the photon is along this path. But where is photon when the state is the combination of the two? You should have guessed by now that we cannot answer this question. What we can answer is the probability of the photon being on either path. This probability is the modulus square of these expansion coefficients. We also call these probability amplitudes. These are the amplitudes responsible for the interference-like phenomena we mentioned a little while back. So the modulus square of iota r gives the probability r square for the photon to be along this path, and modulus square of t, which is t square, is the probability that the photon is along this path. If we place the detectors over here and here, we can verify that these are correct detection probabilities, as we have seen in the first example. The state of the photon after the second beam splitter is obtained by a second matrix multiplication. Again, the matrix for the beam splitter, the state before the action of the second beam splitter, and the state after the action of the second beam splitter. This is the state of the photon just before its detection at D1 or D2. We see that the amplitude along 1, 0 vector, which is associated with this path, is t square minus r square. The modulus square t square minus r square whole square is the probability of the presence of the photon here, and thus of its detection at D1. We already know that this is the correct detection probability and can be verified by performing experiments on the system. Similarly, the amplitude 2 iota
2 iota
RT
RT.
this path gives correct detection probability 4 r square t square for detection at the detector D2. In this way, we see that by using vectors to describe the state of a quantum system, we can compute the experimentally verifiable probabilities and correctly account for the behavior of the system. This brings us to the end of this lecture. Here is a summary of what we have done. We have very briefly looked at the need for quantum mechanics. We have tried to answer the question, what is quantum mechanics? And we have looked at the quantum description of a few simple systems. The lessons we have learned are as follows. Nature at the level of the interactions of building blocks of matter and energy is inherently indeterministic and random. We are not allowed to know when or if an event at this level will happen. We can only calculate the probabilities of the occurrence of these events. Quantum mechanics helps us work out these probabilities by associating vectors to the states of the system. And finally, that the probabilities are the modulus square of the amplitudes expansion coefficient used in writing the state of the system. This is the end of the first lecture. If you wish to read about the examples I have used, you can visit my blog at fahilhashmi.com. And please feel free to post your questions, comments below this video or on my blog. Thank you for watching this video. I hope you have enjoyed it and have learned a few things. Bye.